So let's do one more where we're doing this thing where we split the input in half every time. And then maybe I'll do another one where I have some powers that aren't just 2, but we'll see where we are at that point. So let's say t of n is given by 2 times t of n over 2 plus n. Okay, so this is extremely similar to the last one we did, except now we've got this plus n on the end. And I'll just do what I've been doing this whole time, where t of 1 is c. Right? So once we get down to a trivial case, then we do some constant processing and bubble the recursion back up. So okay, so what do we have? We've got this algorithm that every time it recurses, it cuts its input in half, recurses on both halves of the input, and then in the process does some linear time processing. So this, you can think of this as a linear time overhead. And we could interpret this analysis we're about to do as sort of what's the cost of linear time overhead in this kind of an algorithm where we're splitting in half and then processing both halves. Well, we can chase this around, so we can say t of n equals 2t of n over 2 plus n, plus n. And I'll make my auxiliary equation over here, 2t of x over 2 plus x. And the only subtlety is now we have to make sure that we're careful to add in whatever whatever n is, or whatever the argument is, we have to replace that in all the x's, including the one that's outside of the input for t of x. So here we need to find an expression for n, or t of n over 2. So let's work this out. So we have t of n over 2. Now x is going to equal n over 2. We have 2t of n over 4 plus n over 2, right? When that's that x that was added on the top there. So now we can substitute this back in. And here's where the bookkeeping will kill you if you're not careful, right? It'll lead you completely off track if you're not very, very meticulous about keeping track of what belongs where. All right, so this is 2 times, and then I'm going to substitute in my entire expression here into this. So this is going to be 2 times t of n over 4 plus n over 2. There we go. Plus n over 2. Right now, close bracket, plus n. And so now you can see already we're going to run out of space. So I'm actually going to move all of this over a bit, just to make sure that we don't completely run out of space here. So what do we have? Let me simplify this. Well, the 2 goes in here and we end up with a 4, t of n over 4. And the 2 multiplies by that n over 2, and the 2's cancel, so that's nice. And we end up with n plus n. So we have one n from the very first recursion, and we have a second n from the second recursion. So what this says is that in the big picture, every time we recurse, no matter how many times we have recursed so far, we'll have an additional n overhead, right? An additional linear overhead, where that linear is linear in the original input of the problem. So let's carry on the analysis. I'm going to do one more step of this, even though the pattern is probably already obvious. So one more step of this is going to say, let's let x equal n over 4 now. And so t of n over 4, and we'll have to keep careful track of this expression up here. T of n over 4 is 2 times t of n over 8 plus n over 4. Okay. So now I'll substitute that back in, being very careful with my bookkeeping. So this is 4 times 2t of n over 8 plus n over 4 plus n plus n. And I'm just keeping track of the n's that I accumulated in my previous 2 recursions. So now to simplify, this is 8 times t of n over 8. So I see what that is, right? That's a power of 2. The 4's cancel again on my n over 4, so I end up with n plus n plus n. So what's the pattern? Well, it should be pretty clear, right? 8 is 2 to the 3, and when we have 2 to the 3, we also have 3 n's added on, right? So what that means is that every time we recurse, we double the number of recursion branches in the recursion tree. We have the input sizes to each of those, and we add on another linear overhead amount. So here we have 2 to the k times t of n over 2 to the k plus now k times n, right? So if you recall a couple videos ago, we thought about how if there's a constant amount of overhead on each recursion, we accumulate k times that constant. Well, here there's a linear amount of overhead on each recursion, so we're accumulating k times that linear, right? So k times n. So the anchoring step is going to work the same as before, so I won't belabor it, but we end up with the anchoring step giving us n equals 2 to the k, which is the same as saying k equals log base 2 of n, 2 of n. And so now I'm going to use both those expressions to simplify this. So in the end, what I'll have, once I substitute my anchoring step back in, once I substitute this back in, I'll end up with n times t of 1 plus n log base 2 of n, right? Where this log base 2 of n goes here, and it's substituted in a k, right? So that, goodness, this k goes here and changes to log base 2 of n. This 2 to the k becomes n here. And so what's t of 1? Well, it's c, so nc plus n log base 2 of n. And so now what has happened? As we executed this algorithm, it recursed and recursed and recursed, and each time it recursed, it accumulated overhead, and then eventually got down to a bunch of base cases and computed all the base cases. So this amount of time here is the total amount of time that was spent in dealing with the base cases, right? So this is total base case processing. And this was the total overhead. Okay, and why does this expression make sense? Well, if we are cutting the input in half every time, we're going to have about log 2 of n recursions, right? So that's what that log 2 of n is. And every time, at every level of recursion, we have n overhead. Okay, so this is the total amount of processing time that was spent computing the splitting overhead. Right, so this is the total overhead time. Okay, and so what is this overall expression in terms of order of growth? Well, n log n is slightly slower, right? It's a slightly less scalable algorithm than n. So this whole thing ends up being n log n. And when we get to the divide and conquer unit, we'll be thinking a lot about how to balance overhead processing with the processing that we actually spend at the base case. And this will be an example of a place where we're spending more time with the overhead than with the others.